Right, so this week we're going to take a look at graphing sine and cosine. We're not going to be graphing tangent, secant, cosecant, or any of the others. Okay, just sine and cosine. Okay, and when we graph them, there's four basic transformations that we're going to learn. Okay, moving a graph left and right. Okay, that's what we're going to do today. Shifting a graph up and down. Okay, we'll look at that tomorrow. And then stretching a graph. Okay, you can stretch it, make it taller and shorter, or you can make it wider and narrower. So four different transformations. Okay. Both sine and cosine are called periodic functions. Okay, periodic functions. Okay, a function that's periodic basically means when you draw it, you kind of see this pattern where it's repeating over and over. All right, so let me just put up a picture of what sine looks like. We're not really going to be doing graphing on the calculator, but I'll use it to kind of just quickly show you some things. All right, so this is called a periodic function, okay? Because if you look at a certain section of it, let's just make it a little smaller. Look at it just from here to here. If I basically copy and pasted what I'm seeing right there over and over, I would get this function. Right? So it's basically this part right here that just repeats over and over. All right? So what we say here is all the y values that you get, right? Which if I make it bigger, maybe you can see. What does it look like the y values are between? Doesn't quite go up to 2, a little bit lower. 1 and negative 1. Okay? That's what the y values are between for the entire function. Okay, starts at 0, heads to 1, 0, negative 1, and then back to 0, and then it starts over again. So those values that I just said are going to keep repeating over that interval right there, that interval in the green box. Okay. So there's a certain set. It's like this width from here to here. That's the width. If you go through that width, you're going to hit every possible value you're going to hit. And then after that point on the green box, it's going to start over. Okay, so that's all a periodic function is. It just starts over after a certain point. Okay, the length of that interval before it starts repeating itself, that's called the period of the function. So it's the length of the interval before it gets back to where it started, and it repeats itself. Okay, so I could take a graph like this, and I could make the period shorter. Okay, if I put in a number like 4x. Now what it's doing is it's going from starting at 0 up to 1, 0, negative 1, and back to 0. But it's doing it in a shorter period. Okay? I have to look at a much smaller interval before it starts to repeat itself. Okay? And I could also take and kind of do the opposite. Okay, what I've done this time is I've stretched out the interval. So it starts at 0, up to 1, 0, negative 1, and then it'll go back to 0. But I've stretched it out so far that now that interval goes off the screen. Right? So we can lengthen or shorten the period or the amount of time before the function is going to repeat itself. Okay, we're not going to look at changing that till Thursday. So what I just did on here, we're not going to do till Thursday. Okay, if you don't mess with the graph at all, okay, you just type this in. Okay, this basic graph. That's the period. Okay, 2 pi radians. What is 2 pi in degrees?
180.
Pi is 180.
So 360.
This is 360. All right. So in other words, think of the unit circle. To go all the way around and get back where you started, start at 0, go up to 90, 180, 270. When you get to 360, you're back where you started. That's where this number comes from. Right? So once we go all the way around the circle, we're right back where we started. Right? So that's the period of sine and cosine, if you don't put any numbers or mess with it. Okay. Let me show you sine and cosine. Sine's going to be in blue, cosine's going to be in red. Okay, and once the other one comes up, see if you can tell me the difference between the two. What do you think the difference is? They're not really that much different. You see? Yep. Take. Yeah, so yeah, okay, it's the red one starts at 1, the blue one starts at 0. Do they each have the same height? Yeah. What could you do to the blue one to make it into the red one? Yeah, if you just shifted it. Okay. If you took the blue one and just shifted it to the left, it would become the red one. Okay. In fact, that's all sine and cosine is. Take one and just shift it a little bit and you get the other one. Okay. But both of these have a period from 0 to 2 pi. That's the length before it repeats. If you were to continue to graph it after the period, you're just graphing the same thing over and over. Here's an example. This is 0, this is 2 pi, and this is sine. If I continue this graph, it's just going to be the same thing repeated. Okay, so sometimes they'll ask us, what's the period of this graph? In other words, how far do you have to go before it's going to start to repeat? Okay, for every problem we do today, it's going to be 2 pi. Okay, that's not going to change. Okay, another name for a period, it's also called a cycle of the graph, one cycle. So this is one cycle, what I just highlighted in blue. When I have you guys make a sketch, I'm going to have you just draw one cycle of the graph. Just like any sketch, we got to decide how much we're going to do and then where we're going to stop. Okay, so we stop after one cycle. All right, so my electrical people, cycle. Do you use that to measure anything, especially like cycles per second? Where do you use that?
Usually the frequency for electricity.
Yeah, when you measure the frequency of a wall outlet, okay, it's measured in cycles per second, which is also named after someone. Does anyone know what the name is? Hertz. Yeah, it's measured in hertz. Same with sound frequencies. They're measured in hertz. Okay? That's how many cycles the frequency is doing per second. Right? So 1,000 hertz as a sound frequency means that it's doing this 1,000 times per second. With a sound, if we make this 2,000 cycles per second, it would change how we hear it. Okay, we'll see later in the week, would it make it louder? Would it make it higher pitch? Okay, we'll see what that would do. With your wall outlets, they all have to run at 60 hertz. Okay? That's alternating current. It alternates 60 times per second, or 60 cycles per second. Right, so you do see these kind of measurements other places. We're not going to use cycles per second, though. Okay, we're just going to stick with the word period, okay, rather than cycle. Anytime we graph a trig function, I'm going to ask you to find what's called the 5 critical points, or the 5 important points, 5 key points. Okay, for sine, it's where it starts, where it stops, the highest, the lowest, and then right in the middle. If you can find those 5 points, it gives you a pretty good picture of what your curve looks like. Right, it's a little more complicated than graphing a line. Okay, with a line, you'd only need 2 points. With this kind of curve, you need 5 at a minimum to get a good sketch. Anytime we graph a transformation of sine or cosine, first thing we always have to figure out is where did it start? Okay, if we can't figure out where it's going to start, we can't figure out where it's going to move to. It's kind of like if I said, okay, take the map and go 10 miles north. Well, if you don't know where you started, you can't tell me where 10 miles north is. You got to know where you start from. So I'm going to give you what I call the original tables. I'm going to give you one for sine, one for cosine. And these original tables never change. These are always going to be the starting points. Anytime you have to graph sine or cosine, start with these values. Right, so we're starting at 0. And what did I say we end at? How many degrees do we go through before it repeats? 360, or I'll do it in degrees, but I'm going to write it in radians in a minute. And what's halfway between 0 and 360? You get 180. Halfway between 0 and 180? This one's 90. And halfway between 180 and 360? 270. Those are going to be the x values we use, except I'm going to do them in radians. Pi over 2, pi, 3 pi over 2, and 2 pi. Okay, the reason we're going to pick these x values is because it separates the graph equally. We're basically putting a point every 90 degrees. And that gives us those nice 5 points. Right, and this graph is actually pretty accurate. So let's see if we can use this graph. When x is 0, how high or low am I on the y-axis here? 0. When x is at 0, y is at 0. Okay, how about when I'm at pi over 2? How high up am I on the y-axis there? I'm up at 1. Okay, so pi over 2, I'm up at 1. Zach, how about when I get down to pi? Back to 0. Okay, Callie, how about when I get down to 270? Yep, I'm at -1. And when we get to 360, we're getting back where we started. It's going to repeat now. We're back at 0. So that's your table for sine. And that's always what you want to use as your starting point. So it's very important you have this correct. All right, now cosine, we're going to see the same y values again. It just starts at a different point. Okay, I'll put the graph back up. We'll look at it. Cosine doesn't start at 0 on the y-axis. Where does cosine start when x is 0? What's y? Yeah, let's just put that here so we can see it. Okay. When x is 0, okay, just focus on this section right here. Okay. When x is 0, we're up at 1. How about when we get to 90? Yep, at 90, I know it's a little small to see. When we get to 90, we're crossing the x-axis. How about when we get down to 180? -1. Okay, when we get over to 270, or 3 pi over 2, yep, we're back at 0 again. And then we're always going to end where we started. Now we're back up. Yeah, I drew this a little bit off, but now we're back where we started, up at 1. All right, so if you look at the y values, they're really the same numbers. It's just where did you start? 0, 1, 0, -1, 0. Starts at 0, and then it goes up, back down, hits its lowest, and back to 0. This one starts at its highest, keeps going down till it hits its lowest, and then heads back up. Okay, you can make a reference sheet on the test, so if you want to put those two tables on it, that would probably be helpful. Any questions on those two tables? So this was for cosine. And this graph was sine. And that's what the original graphs always look like. They never change. Okay? Unless you start sticking numbers in, then you can change it.
Oh,
Yep.
okay.
All right, so once we know where the graph is going to start, we've got to figure out where do these 5 key points, all the things I just circled, where do they move to when we transform it? Okay, did they move up? Did they move down? Did they move left? Okay, what happened? Well, for every transformation that we do, one of the 2 columns in the chart you just wrote is going to stay the same. Meaning, I'm not going to do 2 transformations at the same time. If we move it up, that's all we're going to do. We're going to move it up. We're not going to move left and right. If we decide to move it left or we move it to the right, that's all we're going to do. We're not going to move it left and we're going to move it up at the same time. We're going to do one thing at a time. So if we're only going to do one thing at a time, either the x's are going to stay the same and the y's will change. That's one type of problem. Or the other way around. The y's stay the same and the x's change. But you're never going to have both columns changing at the same time. You could. We're just not. All right, so everything up to that point, that's basically just kind of background about what a periodic function is and how you graph it. You've got to find the 5 key points. Okay? Now I'm going to talk specifically about our first transformation. And this is the only one we're going to do today. It's called a phase shift. Okay, a very simple way to explain a phase shift is when you take your graph and you move it left or you move it right. That's it. When I had sine and cosine on the calculator at the same time, that was a picture of a phase shift. One of them is the same as the other, just copied to the left or copied to the right. That's a phase shift. Okay, here's another example of a phase shift. I took that graph in blue, and I translated it to the left, and I used a different color so you could see it. Notice if I keep shifting it so far to the left, it actually lines back up again. So if you phase shifted this by 360 degrees, you can't even tell. There's no difference between 360 and 0. You want to see how they look the same? All right. So that's a phase shift, just sliding left and right. Okay, and what does a phase shift look like? Okay, a phase shift is when you take your original equation and you add or subtract a number inside the parentheses. It could be sine or it could be cosine. Right, so here's an example of a phase shift. That's what a phase shift would look like. I added or subtracted a number inside the parentheses. Most of the time, the number you see right here, it's going to be one of 3 things. Pi, pi over 2, or pi over 4. Just because those are common numbers. Pi is 180, pi over 2 is 90, pi over 4 is 45. So when we shift something, we're usually going to shift it by one of those degree amounts. Okay. But as you can see from the picture, you could shift by 56.8 degrees if you wanted. We usually stick to nice numbers. All right. So there's a 45-degree shift, close as I can get it. That's a 90-degree phase shift. Can't quite get 90. And then a 180-degree phase shift. About right there. Those are the three we generally do. Okay, when you do a phase shift, you got two options. It's either going to move left or it's going to move right. Right. So if you follow these two rules, it'll tell you exactly what's happening. If you have x minus, and then you have a number after it, that's going to shift your graph to the right. Okay, x minus a number. That will shift it to the right. Okay, what do you think it's going to look like when I shift left? It's not going to be x minus a number. Yeah. It's going to be x plus some value. Right, so in the example I wrote up above, this is a shift to the left because it has x plus. Okay, and how much does it shift? Well, whatever the value you put here. If it's pi, it's going to shift left by pi. If it's pi over 2, it shifts left pi over 2. So let me show you, I'll just give you a quick example on the calculator. Let's graph sine of x. Okay, there's just the basic graph, nothing done to it. Okay, now if I take and let me shift that graph, let me shift it to the left. Okay, so if I want to shift left, would I put in a plus or a minus? Yeah, I'm going to put in a plus. Okay, and I'm going to do it in radians. Okay, because that's what we're working in this week. I'm going to shift it left 90 degrees or pi over 2 radians. Right, so I just basically, it's like putting in plus 90 if you did it in degrees. Okay, and let's look at it. You want to see how it shifted to the left? Before it went right through the origin. Now I shifted it left. What graph does that look like? It is. That is cosine. If I graph that and I graph cosine at the same time, they're exactly the same thing. So what I'm showing you is that if you take sine and you push it to the left a little bit, it looks exactly like cosine. Can't even tell the difference. Okay. Any question on that? So last thing before we can try an example, we got to figure out where those 5 key points are going to shift. All right, so phase shift. Okay, we're moving things left and right. If you move left and right, what values are you affecting? Does that affect things on the x-axis or things on the y-axis? If you move left and right, which axis is that? That's your x's. Okay? So for this problem, the y's are not going to change. So those 2 original tables I gave you, right at the beginning, all the y values are going to stay the same every time we do a phase shift, because you're not shifting up and down. If you shift up and down, that's going to affect the y's. Okay. So all you got to do is copy those down from the original table. Okay, if the y's are the ones that are going to stay the same, the x's are the ones that are going to change. So how do we find the new x's? All right, so let's just look at a sample problem. Y equals sine of x minus pi. First thing I got to do is look at what's been added or subtracted. In this case, they subtracted pi. All right, so that's the first thing. Figure out what they added or subtracted. and then do the opposite of that. Okay, this is one it's a little tricky. You got to remember to do the opposite. It's just the way it works. So what I'm going to do is, instead of minus pi, I'm going to do plus pi to every one of the original x values on those tables I just showed you. I'm going to add pi. That's how you shift it left and right. Just look at the number that comes after right there and do the opposite of what you see. Okay, out of the 4 transformations we're going to study, 2 of them you got to do the opposite of what you see. 2 of them you do exactly what you see. The ones you do exactly what you see, I like those better because it makes common sense. All right, this is one that doesn't really make common sense. Why would you do the opposite? It's just that's the way it works. All right, so if I see a minus pi, I'm going to add pi to each of the original x's in that table. Okay, if I had a problem like x plus pi over 2, okay, in this case, I see plus pi over 2, I'm going to do the opposite. I'm going to minus pi over 2 from all the original x's. And we'll go through maybe 2 or 3 examples. First one we're going to try is this one, sine of x minus pi over 2. Okay, on the test, the first thing you're going to have to do is figure out what kind of transformation is it. Okay, this is a phase shift. It's the only transformation we've studied. The way you tell something is a phase shift is you've added or subtracted a number inside parentheses. That's the key. This would be totally different. That's completely different. It's got to be in parentheses to be a phase shift. Without parentheses, we'll talk about what that does tomorrow. All right, so what I did for this one is I copied down the original table. That table right there is just this table right here. I just copied it so we could look at it. First thing I'm going to do before I even sketch it, I'm going to make my new table. Okay, and the table has 10 values I need to fill in. 5 for x, 5 for y. Okay, when you do a phase shift, which column stays the same? The x's or the y's? Yeah, the y's. All the y's stay the same. So we're going to copy those down from the original table. 0, 1, 0, negative 1, 0. All right, so y's stayed the same. X's are going to change. I'm going to take all the original x's. 0, pi over 2, pi, 3 pi over 2, and 2 pi. And I'm going to do something to every one of them. I'm going to do the same thing to all of them. And it has to do with this right here. What am I going to do to every one of those x values?
Add pi over 2.
Yeah. I'm going to look at what's been added or subtracted. In this case, I subtracted pi over 2. I'm going to do the opposite of subtract pi over 2. I'm going to add pi over 2. Okay, to every one of them. And I'll put all my answers in that table. Okay, that's all that I'm going to be focusing on when I grade your problem. What did you get after you did all your work? All right. First one's not too bad. What's 0 plus pi over 2?
Pi over 2.
Just pi over 2. Okay, we're going to leave it just like that. I don't care what the decimal is. We're not going to find the decimal. Okay, next one. We got pi over 2 plus pi over 2. What's that add up to?
2 pi.
2 pi over 2. It's just like adding up 1 over 2 plus 1 over 2. It's 2 over 2. Right? Well, this is pi over 2 plus pi over 2. 2 pi over 2. 2 pi over 2, but I can reduce that one. So what does that reduce to? Pi. Okay, the next one. Pi plus pi over 2. What's the denominator been on pi? 1. Okay, to add these together, what do I need?
The same.
Yeah, I got to have the same denominator. Chris, what's the common denominator between 1 and 2? 2. So what would you multiply the top and the bottom by to make this 1 a 2? We're going to multiply by 2 over 2. Okay, this is just kind of scrap work you can do off to the side. So you got 2 pi over 2 plus 1 pi over 2. And Charlie, what does that add up to? Yep, 3 pi over 2. Very good. Yep, 3 pi over 2. Okay, you keep the denominator the same. Just add what's in the top. Nathan, what's 3 pi over 2 plus 1 pi over 2? If it reduces, don't reduce it yet.
Is it 3 pi over 4?
So keep the denominator the same and just add what's in the top.
4 pi over 2?
4 pi over 2. Yep. Everyone see that? Keep the denominator the same. Just add what's in the top. 4 pi over 2. And Nathan, what does 4 pi over 2 reduce to?
2 pi.
2 pi. Always reduce it if you can. Okay, and the last part, Derek, what's the denominator here even though it's not written?
1.
1. Okay, can I add those the way they are?
No.
No, I got to do the same thing Ben told us earlier. I got to get that common denominator. So John, what's my common denominator again?
2.
2. So I'll multiply by 2 over 2. That's going to give me 4 pi over 2 plus 1 pi over 2. And John, what does that add up to?
5 pi over 2.
Nice. 5 pi over 2. And there's all our answers. Okay. The way I'm going to grade this is you get 1 point for each one of these you get right. So for the y values, you didn't even have any work. You just had to copy them over correctly. The only mistake people usually make with the y values is they'll copy them from the wrong table. Okay, you've got 2 tables, one for sine, one for cosine. Make sure you use the right one. This is a sine problem. All right, so 1 point for each y value, 1 point for each x value. Okay, last thing I'll do is have you graph it. And the graph is going to be worth 2 points. Okay, the graph is only worth 2 points. Okay, make sure you label your axes. And we're not going to label them 1, 2, 3, 4, 5, 6 because these decimals would be awful to work with. Okay, pi is like 3.14. Pi over 2 is 1.57. So I'm going to label my axes using these values. That's going to be pi over 2, pi, 3 pi over 2, 2 pi, and 5 pi over 2. Okay, you can label your axes any way you want, as long as you keep everything equally spaced. And if we did these in degrees, I guarantee everyone would see these are nicely spaced. 90, 180, 270, 360, 450. It's just plus 90 each time in degrees. And now graph your points. Pi over 2, 0. Pi, you're up at 1. Let's see, 3 pi over 2, back to 0. 2 pi, we're at -1. And then 5 pi over 2, back to 0. Okay, when you connect them, try to make it look curved. This graph shouldn't look like that. Everything should be somewhat nicely curved. Okay, and that's a phase shift. Any questions on that? All right, so on the homework, what I'm going to do is have you sketch the original and then have you sketch the final. The original would have been like this.
Where are you going so long?
Not yet. Okay, in red, that's the original. In blue, that's the new one. It's been shifted to the right by pi over 2. And that's exactly what should have happened. Anytime you do a minus, it should shift right. All right, let's try one with cosine. All right, so now when you copy down your original table, make sure you're looking at cosine. Don't look at the sine table. Okay, first thing I like to do right away, identify what kind of transformation this is. Okay, Andy, anytime I add or subtract inside parentheses, it's always a phase shift. And what stays the same for a phase shift I can fill in right now? Yeah, y values are going to stay the same. Okay, so we go to that original table, and we're going to copy down all the y values. Dakota, can you give me my y values for cosine?
1, 0, negative 1, 0.
Perfect. 1, 0, negative 1, 0, 1. If you can do that, you get 5 points right there. Just for that. 5 more points if we can get all the x's. Okay. I like to write down where they start. Okay. And the x's are 0, pi over 2, pi, 3 pi over 2, 2 pi. I'm going to put all my final answers in that box. Okay, Chris, what am I going to do to every one of these x values?
Minus pi.
Perfect. We got a plus pi. Phase shift is one of the transformations. Do the opposite of what you see. Okay, so minus pi. Paige, what's 0 minus pi?
0.
If we did 0 minus 0, we'd get 0. But this is 0. Think of it as like 0 minus something. What do you get?
Would it be pi?
Negative pi, right? Get negative pi. Okay, anytime you take 0 and you subtract something, the answer is just whatever that negative something is. Okay, next one. Alex, what's the denominator under pi right now? 1. And what's my common denominator? 2. So I'm going to multiply top and bottom by 2. What's 1 pi over 2? Take away 2 pi over 2.
Negative pi over 2.
Yeah, he's going to write it out, but you got it. Nice. 1 pi over 2, take away 2 pi over 2. 1 take away 2 leaves me with negative 1. Or you could just write negative pi over 2. Okay, next one, Nick, what's pi minus pi?
0.
0. So that's a quick one. And the last one we have to find a common denominator for. It's going to be 2 again. Multiply the top by 2 and the bottom by 2. Zach, what's 3 pi over 2? Take away 2 pi over 2.
1 pi over 2.
And the last one. Well, Ashley, what's 2 pi? Take away 1 pi.
Pi.
Just pi. Okay, and if you look at our table, let's look at the last one too. There's kind of a pattern to the values you get. Okay, on the last problem we did in blue, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. What do you think the next one would be if we did one? 6 pi over 2. And the next one? 7 pi over 2, 8 pi over 2, 9 pi over 2, 10 pi over 2. That pattern would continue. Okay, once we reduce the fraction, we don't see the pattern as easily, but it's still there. Okay. This one, if we had common denominators, this would be negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. Just keep continuing. All right? We're not going to continue it, though. We're just sketching one cycle. All right, so that's another way. When you get your table, see if you see the pattern. Sometimes if you see it right away, you don't even have to do the common denominator. You just look for the pattern. Okay. All right, and make our sketch. Okay, again, make sure you always label your axes. If you don't on the test, I'm going to take a point off your sketch. Okay. All right, and this time we got to go negative with 2 values in the negative section. Okay, so leave enough room for both. This will be negative pi over 2. 0 is the axis. We don't have to label 0. Pi over 2 and pi. All right, so we start at 1, go down to 0, negative 1, 0, and back to 1. Okay, now remember, this is part of a wave. So it shouldn't look like a V. Basically, you're sketching this section right here. Kind of looks like a V, but it's just a little bit more curved. Right, so just try to curve it the best you can. It doesn't have to be perfect, just best you can. And if it was going to continue, it would look like that. Okay, any questions on that one? All right, so we'll try one more, and then I think I'll give you guys some time to start the homework. Okay, the homework is it's just going to be 5 questions. Just 5 questions. Okay, so try that one. See if you can at least make the table and figure out which values stay the same. Okay, if you have trouble with the arithmetic, I'll help you out with that. Okay, but just give that a shot on your own. All right, let's see if we can at least figure out which values stay the same. X's or Y's?
Y's.
Yep, Y is going to stay the same. Okay. You're adding or subtracting in the parentheses. That's a phase shift. You're going to move it left and right. You're not moving it up and down. Okay. Becky, what are my Y values for sine?
0, 1, 0, -1.
Okay. 5 points just for writing those down. 0, 1, 0, -1, 0. Okay. Next, I'm going to put down the original X's, and then I'll write what I'm going to do to them. John, what are the original X values?
0, pi over 2, 3 pi over 2, and 2 pi.
Good. And now, Dakota, we're going to take every one of those, and what are we going to do to it?
Add pi over 4.
Good. So you guys are good. You're picking up that. You got to do the opposite. So you see minus, you got to do plus. Okay, to each one of them. And this is one, if we start to see the pattern after finding 2 or 3 common denominators, let's just see if we can speed it up and do it that way. Okay, 0 plus pi over 4. It's just pi over 4. Right, Kaylin, what's my common denominator between 2 and 4?
2 or 4.
4. Yeah, common denominator has to be at least bigger than all the other denominators, okay, or equal. So in this case, it's 4. And what would you multiply top and bottom by? Yep. So that's going to become a 2 and a 4. Okay, Analia, what's 2 pi over 4 plus 1 pi over 4? 3 pi over 4. Okay, Jackie, common denominator here again will be,
4.
so multiply top and bottom by 4. And what's 4 pi over 4 plus 1 pi over 4?
3 pi over 4. 3. 5.
5 pi over 4. Okay. Anybody think they see what the next one's going to be? Yeah?
7 pi over 4.
7 pi over 4. How'd you get that? What's the pattern?
You add 2 pi each time you go down the x.
Yeah, you're just adding 2 to the number in the top. 1, 3, 5, 7. And the last one?
9 pi over 4.
9 pi over 4. Okay, if you wanted to do the common denominator, you could. Like in this last one, multiply top and bottom by 4. That becomes an 8. Becomes a 4. 8 plus 1, there's your 9. All right, and last thing we're going to do our sketch. Okay, so one point for every one of those. Table is going to be worth 10 points on the test. All right, my sketch. Pi over 4, 3 pi over 4, 5 pi over 4, and 9 pi. Sometimes it gets a little cramped, but just squeeze it in the best you can. Right. 0, 1, 0, negative 1, back to 0. Okay. Any questions on that? Right, so that's a phase shift. Right, so the homework tonight, just going to be practicing phase shifts, and the grids are already drawn for you. Okay, so there'll be a worksheet. I'll try to put the worksheet in the video just in case anybody needs it, but I'll give you a copy right now.